A slightly more difficult example now. A gun at some point 0 fires shells with a variable angle of inclination at 200 meters per second. Let G equal 10 meters per second squared. Find two possible angles of inclination required to hit a target 2 kilometers away on top of a 1,000 meter mountain. Find the flight times, impact speeds, and angles of impact for both options. Now, there's a lot to do here. Start with a simple sketch. So I can see that we've got 2 kilometers and we've got 1 kilometer there. It's tempting to change them both into kilometers so that I can just use simple numbers like 2 and 1. But remember, we've got our gravity in meters per second squared, and we've got our speed at 200 meters per second. So we need to keep everything in the same units. It's going to be easier actually just to work in meters. So if I let the origin be the point that my gun is shooting from, then over here at 2,000 meters away, I've got a mountain, and so let's say the fortress is up there. It doesn't need to look like a mountain, but we need to see that there'll be two possible angles. Perhaps a lob shot might hit it, and maybe something that's lower might also hit it. So we're finding those two different angles of inclination. The other thing that we're given is our initial velocity. We don't know the x dot and y dot components of it, and we're looking for theta. There's going to be two options, but we do know that we've got 200 there. So that means we've got our initial x dot is 200 cos theta, and initial y dot is 200 sine theta. Okay, so now writing my 6 equations. First one, easy. The second one, I can see that I've got it over there. It's my constant of integration at time 0. And my third one, I'm integrating that with respect to t and paying attention to the fact that I'm starting at 0, 0. So when t is 0, my constant will be 0, and so that means I don't need to add anything on there. Now you can write this as 200t cos theta or 200 cos theta t, completely up to you. Now for our y double dot, we've been asked to use -10. So that means that y dot, we need to integrate that with respect to t and then add a constant. And we're considering the fact that when we add our constant, when time equals 0, the constant is going to be this. So that means that we can add that on as our constant. And now when we integrate that with respect to time, we get minus 5t squared plus 200 sine theta t. Now the only reason I'm putting brackets around that whole thing is so it doesn't look like the sine of theta t. And perhaps that's a good reason. In fact, let's go ahead and do that. Let's write it as 200t sine theta this time, just to make sure there's no confusion. It saves us using the brackets. We could do the same thing up here if we want to. 200t cos theta. Doesn't really matter which way you've gone, just whatever way makes sense. And now we've got our 6 equations there ready to use. Now I'm going to start by saying we know that when x is 2000 and y is 1000, we want to find what t is. Now we can't directly relate these together because they've got different formulae. So this is a little bit like when we were in year 11 solving parametric equations. T is the parameter here. Now there's a couple of ways that you can do this. We're effectively solving them simultaneously. The easiest way to do that, I think, is to let x equal 2000 and get yourself an expression for t. Now it's going to have an unknown in it because we don't know what cos theta is, but we can then sub that into the other equation so that we can get so that we can actually solve for theta. So let x equal 2000, and now we've got 2000 is equal to 200t cos theta. Now to get the t by itself, we just need to divide both sides by 200 cos theta. So we can say t is equal to, well, let's do it. I was going to do it in my head, but that's okay. Let's just put it all in there. So that is equal to, we can cross off some zeros here and divide, and we can see that we've got 10 over cos theta. All right, so when the time is this, that's when y is going to be 1000. So now we can sub that in. When t equals 10 over cos theta, y is equal to 1000. So therefore, let's write our equation for y. 1000 is equal to -5. Now we need to square t, so that means we need to do 10 over cos theta, all squared, plus 200 times t times sine theta. So we've got 200 t. Oh, actually, let's do the sine theta first. I actually prefer it that way. And then let's multiply that by t. Now, multiplying by 10 over cos theta. All right, this is going to get messy, and often they do. The process you need to follow through is relatively straightforward, but the maths that you need to do could get you a little bogged down. So just persist with it, tidy it up as best you can. All right, so next we can say we've got 1000, and here we're squaring the 10 to get 100. So we've got -500 over cos squared theta, because I've had to square both parts of this fraction. And now I can see I've got 200 times 10, so I've got 2000, but I've also got sine theta over cos theta, and that's going to give me tan theta. Now, quick inspection here. We've got tan theta, and we've got cos squared theta sitting on the bottom of a fraction. We need to get it all in terms of sine, cos, or tan, and it's looking like we've got something squared, something not squared, and some numbers. It's looking like a quadratic. So firstly, we're going to need a little bit more space. Now, how do we get these into the same ratio? Well, cos squared being on the bottom of a fraction, that's 1 over cos squared theta, and that's sec squared theta. Can that talk to tan in any way? It can, can't it? So if you're thinking of a Pythagorean identity, this one is on your reference sheet. And then to create the one that's got tan in it, we can think, all right, we'd have to divide all of the terms by cos squared theta. So we'd get this. Okay, so we can use that and say this is -500 sec squared theta. So on the next line, I've got 1000 is equal to -500, but I'm not going to write sec squared theta. I'm going to write tan squared theta plus 1. And now I need to add 2000 tan theta. I'm running out of space a bit here. 2000 tan theta. All right, what next? Next, let's expand these brackets and maybe get everything onto one side. So looking at my tan squared theta here, I've got -500 tan squared theta on the right-hand side. So if I add that to both sides, then the left will start with 500 tan squared theta. And now I've got 2000 tan theta on the right, so let's subtract that from both sides, and I'll have -2000 tan theta over here. And here I've got -500 times 1, -500. So if I add 500 to both sides, then I've got +1500 equals 0. Just squeezed it in. All right, let's divide everything by, well, we can divide by 100, but we can actually divide by 500. So now we've got tan squared theta -4 tan theta plus 3 equals 0. And that tidied up a lot in that step. So now I can see how to solve this. If you want to let u equal tan theta, you can, and then solve it. I can see here that I can just go ahead and put my tan theta in, 2 sets of brackets, and I need 2 numbers that multiply to make 3 and add to make -4. So I need -1 and -3. So that means that tan theta is equal to 1 or 3. And that means that theta will be the inverse tan of 1 or the inverse tan of 3. Now the board got a bit busy there, so I've cleared this side. I've noted down my 2 angles that are going to allow me to hit the target. I've got my 6 formulas, a reminder of what I'm doing over here, and my formula there for the time to hit the target. Now, if I want to know the time to hit the target, I've just got to sub each of my angles into this formula. But this one was the inverse tan of 1, which we reasoned was exactly 45 degrees. The other one, remember, was around about 71, 72 degrees. And rather than use it in a rounded off form, it makes sense to keep it like this, because then we can actually find the sine or the cos or the tan of any angle we like once it's in this form. Now, for this one first, we've just got to sub it in. So t is equal to 10 over the cos of 45 degrees, which is equal to 10 over 1 over root 2, which is 10 times root 2 seconds. So that's how long that one takes to hit the target. Now let's keep on going with that one. We know how long it takes to hit the target. What velocity is it going to come in at? So now we need to consider when t equals 10 root 2, what is our x component of velocity and our y component of velocity? Well, our x component of velocity is always the same. It's 200 cos of theta, which in this case is cos of 45 degrees. And the cos of 45 is 1 over root 2. So I've got 200 times 1 over root 2, which is like this, but perhaps a little bit easier to think about if we rationalize the denominator. That'll give us 200 root 2 over 2, which is 100 root 2. So this is the horizontal component of the velocity. And when t is 10 root 2, y dot is going to be minus 10. We've got this here, multiplied by 10 over cos 45. So we're going to have minus 100 over cos 45 plus 200 times sine of 45. And when t is 10 root 2, y dot is going to be minus 10, we've got this here, multiplied by 10 over cos 45. So we're going to have minus 100 over cos 45 plus 200 times sine of 45. Now, that gives us minus 100 divided by 1 over root 2, which is the same as multiplying by root 2. So we get minus 100 root 2. And here we've got 200 times 1 over root 2, and that's the same as 100 root 2. So what we get here actually is 0, because both of these terms are the same but opposite. So what this means is that when our angle is 45 degrees, the lower shot, we're going to come in with a vertical velocity of 0, which means that the velocity is completely the horizontal velocity. We're coming in flat at an angle of 0 degrees. So just by finding the impact speed here, I've actually also found the angle, because I can see that there is no vertical component. So therefore, when theta equals 45 degrees, we get a horizontal impact at 100 root 2 meters per second. Okay, so that's that one done. Okay, now to do this other one over here, when theta equals this. Now let's just consider what else we know about theta. If theta is equal to the inverse tan of 3, that means that the tan of theta is 3. And that means we've got 3 over 1 here in a right angle triangle. So that means that 3 squared plus 1 squared would give us root 10 over here. So this is really helpful because it means that for this little formula where we need cos theta, and in other sections where we need sine theta, we can quickly and easily generate it. So we could say here that the sine of theta is 3 over root 10, and the cos of theta is 1 over root 10. And that is super handy. So now we can say that t is going to be 10 over cos theta. Let's just divide it by cos theta, which is 10, divided by 1 over root 10, which is 10 root 10 seconds. And we've got that in exact form. Whereas if we just said, look, it's 10 over the cos of 71 point whatever, even if we had the exact value saved, we'd then have to round it off. Whereas this way, we get it exact. Okay, so then when t equals 10 root 10 seconds, you'll note that this flight takes a little bit longer, and you'd expect that because it's more of a lob shot. It's going to be in the air for longer, so always check that that sort of thing is making sense. We're going to find x dot, and we're going to find y dot for this value of time, and then we can make a little right angle triangle. We didn't need to over here because one of them was 0, so it was a flat triangle, and we'll be able to use that to get Pythagoras and find the speed. So first let's find x dot. It's 200 cos theta, and we've just found what cos theta is. So it's 200 times 1 over root 10, which is the same thing as, let's multiply the bottom by root 10, we'll get 10, multiply the top by root 10, and we've got root 10. Whereas y dot is going to be negative 10t, well, t is this. So we've got negative 10 times 10 root 10 plus 200 times the sine of theta. See how handy it is having that there already, times 3 over root 10. So tidying up, we've got minus 100 root 10, and over here we've got plus 600 over root 10. Now if we multiply the bottom by root 10 here, we'll just have 10, but if we multiply the top by root 10, we'll have that, and then we can divide. So we've got 60 root 10 minus 100 root 10, and that gives us negative 40 root 10. Now, why is our y dash negative? Because our bullet is coming down now, and so its vertical velocity is negative. That makes sense. Okay, now we need to draw up a quick triangle. Let's just use this bit of board space that we've got up here. So we've got the bullet coming in like this, and we can see the x component is 20 root 10. We've got an angle that we need to find, because we're finding the impact angle now, not the takeoff angle. And we've seen that this vertical component is negative 40 root 10. Well, we can just label this 40 root 10 really, because if we're going to use Pythagoras, the fact that it's negative is not going to make any difference. So now we can see that the impact speed is going to be the square root of 40 root 10 squared plus 20 root 10 squared. Now, if we want to get this in exact form, we're going to need to just find out what 40 root 10 squared plus 20 root 10 squared is and put that inside our big square root, because that way we can keep it exact. So let's go 40, I could do this in my head of course, 40 root 10 squared, which is really just 40 squared, 1600 times 10. In fact, let's just do that. We've got 16,000. Is that right? 1600 times 10? Yes. And 2020s is 400 times 10 is 4,000. So what we have in here is 20,000. So the square root of 20,000 is the square root of 10,000, which is 100, times the square root of 2. And that is our impact speed in meters per second. And I think you'll agree it's nice to have it in exact form rather than to have something that's rounded off. So impact speed is there. Now, last thing to do, oops, I've sort of cut that off, is to find the angle of impact here when we're using this angle. So clearly we can just say it's the inverse tan of 40 root 10 over 20 root 10, and that cancels down to 2. So theta is the inverse tan of 2. That's perfectly okay in exact form, but we may as well say that it's also roughly equal to, and then we can put that into the calculator, inverse tan of 2, and we get roughly 63 degrees to the nearest degree. So that's, again, the angle that's coming off the horizontal. So when we're looking at the takeoff angles, I tend to draw my right angle triangles around like this because I've got the direction of motion going to the right, and drawing my impact angles, I've got my components of velocity here and my actual speed on the hypotenuse there. So in an ideal world, I'd have free board space here, and I'd say when theta equals 45 degrees, the flight time is 10 root 2 seconds, and we have a horizontal impact at this speed, whereas when theta equals this, and you could put an approximation in for that if you like, it was 72 degrees or so to the nearest degree, blah, blah, blah. The flight time would be this, and the impact speed is this, and the impact angle is this. So heaps of information there. I haven't set mine out beautifully because even though I've got this big board, if I had a nice piece of paper, I'd just work down. If you've got space and you're looking at two different things, you can do them side by side in columns. But I highly recommend putting a box around things when you've found them, especially your 6 equations that you're going to use at the start, and then each piece of information. And constantly refer back to the question to check if you've actually answered it.